Hello, this is T Chapman 500, and this is Ben Eater's CPU in Logism Evolution, a highly modified version of Logism Evolution. Link in the description. I tried to recreate Ben Eater's CPU in Logisim as exact as possible, although I did make a few adjustments. First off, the last video I can find does not have a jump carry instruction or an add immediate instruction, so I added those. And the jump carry works perfectly. And secondly, I'm having to deal with the limitations of Logisim, so these three ROMs basically have to be here because I can't use a multiplexer with a single ROM and guarantee that all four of these displays will be lit quickly enough for them to actually visibly appear to always be lit. And I also added an instruction set reference right into the simulation. So this will help me program the computer. So let's start off by making a basic program. So now I've enabled the main clock. It's running right now at about 100 Hertz. Take this number right here, divide that by 2, that's the actual speed of the clock that's running the system. So now I'm going to start programming a very basic program. Don't want to get too complicated. So first off, I want to load immediate, so that's 0101, and the value will be 0. Pulse the clock, change the address, then add immediate, which is 1000, then the value would be 1, pulse the clock, next address will be output, so 1110, and the second 4 bits would be all zeros. And finally, unconditional jump to address 1. So that is the entire program. So this counter right here is going to start counting from 0 to 255, and then it's going to loop back to 0. Let's start the clock running. That's not supposed to happen. There we go. So now it's counting from 0 to 255, and I can even set it to a signed number, so now it's going to count backwards. Well, not backwards, it's now going to count from negative 128 to positive 127, and here's an interesting fact. With an 8-bit number, negative 128 and positive 128 have the exact same binary representation. So let me speed up this clock. So now it's going very fast. Let me also load something else. This is Fibonacci. It took a while for me to program, particularly since I had to minimize the number of instructions because I only have 16 bytes to work with. Now, one thing I would like to see in a future video by Ben Eater is to expand the memory space to 8 bits and separate the data and address bus. So this is Fibonacci. It goes all the way up to 233. That's the maximum Fibonacci number that can be represented with an 8-bit value. So let me switch it to signed and slow this down. There we go. So 112, 23 are the only two negative numbers that can be represented in an 8-bit Fibonacci number. And then there's let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 Fibonacci numbers in an 8-bit number, and it really doesn't go that much higher with additional bits. So I'm gonna load a CPU that I've been working on in one moment. We are now in the CPU that I'm designing, and if you'll notice, it has a 16-bit data bus and an address bus. So it has 65,536 unique addresses for a total of 128 kilobytes. It's not complete yet, but on my last attempt to make this video, this GPR block wasn't there, and neither was the arithmetic logic unit, although I am going to have to redesign the arithmetic logic unit. If you'll notice, the upper half label on the ALU, that is for the upper half of the multiplication, right here. This is by no means complete, and it's gonna be redone a bit. So let's go back to the core. There's nothing in the main, but I want to show the instruction unit, the control unit. The instruction comes from the top, is split up into 3 different fields, which are then sent out the top. We have the main clock, which is a frequency division of the step clock. The stepper just has a 3-bit counter and a D flip-flop for the clock. And if you noticed, we also have a clock counter. This is basically comparable to Ben Eater's stepper, except the stepper on this computer CPU counts basically fractions of a clock cycle, whereas the stepper on Ben Eater's CPU counts clock cycles. And if we look at the data lines or the control lines here, we can see that we actually have control over when the clock counter is reset. We can dynamically reset the clock counter. Some instructions use only the first output of the clock counter. The moment the second output goes high, it's reset. Other instructions can use more than the first output. Whenever it goes beyond the last output that's used, it resets. So for example, the move instructions use 2 wires from the clock counter, and the 3rd wire triggers the reset. I do have a sheet of paper somewhere that describes almost all the signals that I'm using in this CPU, and there are 37 of them so far. Now, the instruction is split up into 5 different fields. The instruction class. If the class is 0, then it's something that the control unit does to, say, set up for another class of instruction. Class 2 is for the arithmetic logic unit. Class 3 is going to be for the floating point unit. The operation describes the operation that the CPU is going to perform. And the always 0 field actually goes to the destination register, and it's always 0 when the destination is not in use. But other than that, this field is ignored, and the value in the destination field is sent to the registers. The source A and source B fields allow you to select up to 2 registers. For example, adding A and B, then stores it in the destination. And if we trace the source A, we'll find that it's actually the sub B field. And if we trace the source B wire, we'll find that it's actually the sub A field. So that's what I have so far of this CPU, and I believe that will be the end of the video. Hope you enjoyed it. I hope to be doing future videos with this processor. And next time I show this processor, I hope to have at least something going for the arithmetic logic unit, and perhaps some more stuff like the address register block. This is T Chapman 500 signing off.